Hey, thank you. Any other comments from the coordinators? Any other comments? Going once, going twice? Okay. Now we're up for our topic tonight is antennas, which are way over most people's heads, as they should be. That's a bad pun. That's a lead in. Okay, Jim, it's all yours.
I always say start with a joke, right? All right. So some of the feedback that we got was members were interested in learning about antennas and kind of not the super deep down in the weeds level, and so this is, I kind of put it, for new hams. It's information about antennas that's accessible to folks that are just getting started. So we're going to be kind of at what I call the 25,000 foot level. Go ahead, next slide. So what is this presentation not, right? I'm not going to stand up here and work through Maxwell's equations. This is not a, hey, this is the best antenna, go buy this antenna, go build this antenna, spend the money, go put up your tower, right? What this is intended to be is kind of what I wish I knew when I was starting out, right? So what are every antenna is a compromise, right? And understanding all the things that go into those compromises so that you can make choices based on what you have available, so you can get kind of the antenna that's going to work the best for you in whatever your situation is. And so again, we'll kind of talk about some of these compromises, right? Not everybody has the same amount of land that's available. Some antennas, depending on what frequency you want to operate, are hundreds of feet long. Support structures, not everybody's going to be able to get their antenna 880 feet up in the air. And then, available budget, right? That's always going to come into decisions that you're going to make when you're starting out. All right, next. All right, so a little bit of background. Go ahead. So what is it that we're trying to capture with our antennas, right? So when I was growing up, I always had somebody say, you don't learn about deer hunting studying rifles, right? You study the animals that you're hunting, right? So what are we looking for? We're trying to capture these things, electromagnetic waves. And so a radio wave has both an electric field and a magnetic field. And you see my fancy little animation here. That's moving along through space. And so some guy named James Clerk Maxwell back in the 1800s first came up with a set of equations that describe how these things move, right? And he had 20 equations and 20 different variables. So that right there kind of gives you a hint that there's a lot that goes into antennas. And so trying to bring it down a level and make it a little, kind of simplify it a little bit. Another mathematician later on figured out how to get those 20 equations down to 4, but it's math that I rarely tangle with. But it comes down to, there's 2 components to your radio wave. There's your electric field, which you can see in the blue, a magnetic field, which is in the red. And in general, both of these fields contain the same amount of information, right? So when we're thinking about our antennas, we don't need to worry about capturing both of them. All right, next. Oh, the other way. So here's kind of some basic terminology. This is another area that when I was getting started trying to sort out all the jargon from the terminology and what, the various words that you hear thrown back and forth. So we'll see resistance. And this is, not a formal definition of it, but it's more of what I call a working definition. This is what it means to me, right? So a resistive element, the kind of thing to remember is it dissipates energy, right? So like a resistor in a DC circuit resist current, it'll get warm. So you're dissipating energy with resistance. Reactance is that funny thing that shows up in AC circuits that kind of acts like a resistor, but you don't dissipate energy with reactance. And so we'll get into that a little bit further down. And so then when we're thinking about our antennas, you'll hear this word impedance a lot, right? Because the impedance of your antenna matters, and you need to be able to match that impedance to your radio. So what is impedance? Impedance is just a combination of this resistive element plus the reactive element. Most of our antennas are compared to what we call the isentropic antenna. This is that fictional perfect antenna that radiates perfectly in all directions. It's kind of like the frictionless pulleys you learned about in physics class. It doesn't exist, but it's kind of the basic unit of comparison that we use when we're talking about antennas. Directivity. So antennas have some pattern which they radiate. An isentropic antenna has no directivity. It radiates perfectly in all directions. Not perfect antennas have some degree to which their radiation pattern is not uniform. It'll radiate more strongly in one direction than another. I tend to refer that as directivity. Some people call this gain. I think directivity is a little bit more descriptive about what's actually going on with the antenna. Wavelength. So when we were talking about our electromagnetic waves, there's a frequency associated with that. And so the frequency, as you saw in the previous illustration, is you've got your wave that's oscillating, and for it, the distance that it travels and the time that it takes to go through one full cycle is the wavelength. And so a lot of times wavelength comes up when we're talking about how big our antenna needs to be to operate on a specific frequency. We'll see decibels a lot. Decibel is a unit of measure. It's relative, right? So when you hear decibels, you think that, okay, this is a quantity that's being compared to something else. And so a lot of times you'll see a little letter here after dB that tells you what your reference unit is. So dBi would be reference to this isentropic antenna. dBm is usually a milliwatt. dBw is usually reference to a watt. There's a whole bunch of them out there, but that's kind of what that means. Resonance, this comes up quite a bit. Resonance just means that the reactance is 0. And then a match. And so these terms, especially when I was getting out, seem to get kind of conflated, right, between resonance and match. Match is when your source impedance equals your load impedance, which is not necessarily resonance, but we'll get to that in a little bit more. All right, next. All right, so before we get to antennas, we need to really kind of think about how our radio waves move, because that's going to dictate what kind of antenna is going to work better. And so we start off with ground waves. Ground waves are kind of the predominant mode for propagation when you're talking about tens of kilohertz up to about a megahertz. So think AM broadcast in the US, most of that travels by ground wave. As you go up in frequency, you start getting to where the skywave is going to be your predominant mode of propagation. And so that's into the ham band, so kind of 3-4 megahertz on up to 30 megahertz. That's going to be your predominant mode of propagation. Ground wave still exists at those frequencies. It just doesn't travel nearly as far. Sometimes you'll hear people talking on like, oh, I must have you on ground wave because they're two stations that are relatively close to each other. But you can see it's kind of through the illustrations here. Skywave, it's bouncing off the ionosphere. So you'll hear a lot about the skip zone, because your signals are going over the heads of some folks here in the middle. So that's something to take into account when you're thinking about what antenna and what frequency is going to be best for who you want to communicate with. And then finally, as we get even higher, we get into what I call line of sight, where basically you have to have an unobstructed path between two antennas in order to communicate. And that becomes kind of the predominant mode for VHF frequencies and higher. There are some exceptions. So you hear about sporadic E. So that's kind of a skywave mode at the VHF level. Ducting, some of the, especially once you get up into microwave, the microwaves will actually follow humidity ducts in the atmosphere. So you can get over the horizon propagation that way. But these aren't reliable, right? They're not something that happens. So if you want to just pick up your radio and talk to somebody on VHF, you can't count on these other modes being there, right? All right, next slide. So I kind of included this just as a note because you see a lot of decibels out there, and instead of going through the math at how you calculate a decibel, I decided to just give you a few shortcuts here. So if you see 3 decibels, that means a factor of 2. So if your gain goes up by 3 decibels, that means you've increased your power or increased your directivity by a factor of 2. To get to 4x, that's 6 dB. So decibels add, whereas linear is multiple. So your S unit on a receiver is typically 6 dB. So that means 1 S unit is about 4 times stronger received signal. 10 dB is easy. 10 dB is 10x. And this one you don't see quite as much. But if you do the math, it's not exactly 25%, but roughly. So if you see that your cable has 1 dB of loss, you can say, well, that's kind of approximately 25%. It's not exact, but so those are just some shortcuts to kind of keep in the back of your mind as you're going through this. All right, so we'll get into some of the basics. Apologize, the print here is a little small, but kind of the first is how do antennas work, in the first place, right? And it all comes down to the electrons in whatever conductive material you're using to build it. So if you place an electrical potential across a conductor, the electrons in that conductor are going to be attracted towards the positive charge. Moving electrons generate a current, and a current generates a magnetic field. And now you've got both components of your radio wave. You've got your electric field and your magnetic field. Conversely, if you place a conductor in a moving magnetic field, the electrons will start to move perpendicular to the lines of magnetic force, called the flux, right? Once you have moving electrons, now you've got a current. And if you put a resistance, a finite resistance in that current, it generates a voltage. So now you're back to potential, right? So our antennas work kind of in two modes, either an electric potential or a magnetic field. And then the important thing to remember is for radio, we only need to interact with one of those two fields because they both contain the same information. So electric field, you're thinking dipoles, quarter wave whips, those sorts of things. Magnetic fields are your loop antennas. And so some of the general properties antennas have, one of them is scaling. So if you design an antenna for 40 meters, it works at 7 megahertz, and you think that's great, boy, I'd love to have this antenna work at 30 megahertz. All you have to do is scale it. You can actually make it that much smaller, just proportional to the frequency increase. And in general, most antennas are reciprocal, not all of them. There are some antennas that are only good for receiving, but in general, if you have an antenna that you can transmit with, its receive pattern will be the same as its transmit pattern. That's kind of what that means. All right, so one of the other things we need to think about for our antennas is polarization. And just by convention, we could say the polarization is the alignment of the electric field. So the blue wave there on the thing, that's our electric field. And we say when the electric field is perpendicular to the earth, not ground, the earth, the dirt that we stand on, we're going to call that vertically polarized. If that electric field is parallel to the earth, we call that horizontally polarized. And then there is such a thing as circular polarization. This is primarily seen in space communications. What happens is the ionosphere will actually cause that electric field to rotate at a constant rate. It can rotate to the right and to the left. So there's two different types of circular polarization. That's a rabbit hole in and of itself. So I just, in mentioning, kind of when you're starting out, you probably don't have to worry too much about circularly polarized signals, but threw it up there for completeness sake. Not quite yet. And so the last thing to talk about polarization, in some systems, the polarization matters. And so if you are using a vertical antenna, vertically polarized antenna to transmit and a horizontal antenna to receive, you're going to lose about 30 decibels of signal. So 30 decibels is about 1,000. So you're going to lose about 1,000. It's 1,000 times less, right? Circular to linear is not as bad. So vertical and horizontal polarization, we call those linear polarizations. So if you're trying to listen to a linearly polarized signal with a circularly polarized antenna or vice versa, you're only going to lose about 3 dB. So that's not quite as bad. All right, now you can go to the next one. Next one the other way. All right, so the first parameter to talk about when we're talking about antennas is impedance. And so when we're first starting out in electronics, we learn about resistors. The value of a resistance is the ratio of the current to the voltage across the resistor, the current through the resistor to the voltage across it. Impedance is similar. It's a ratio of current to voltage. And so that's the important thing to remember here. Impedance, again, we go back to now impedance is there's a little bit more to impedance than just resistance, because you have this pesky thing we call reactance, which shows up because we're using AC or RF in our circuits. Important to remember, it's not constant across your antenna. And so when you look at your basic dipole, if you measure the impedance in the middle of your dipole in a center fed, your impedance is going to be about 70 ohms, and that's assuming your dipole's in free space, right? So that's a perfect ideal dipole. If you move that feed point to where it's no longer in the center, in the case of an off-center fed, now your impedance goes up to about 200 ohms. So that's one thing to think about. That's a trick I've used sometimes in tuning an antenna is if the impedance is not kind of where I need it, sometimes I might make one end just a little bit shorter, and that'll move that feed point just a little bit, and it'll actually change the impedance. And so when we're building our systems, our radio shacks, right? There are three impedances we generally deal with, right? So you have your radio, the antenna port on your radio has an impedance. I think 99.9% of all radios that are sold today have a 50 ohm antenna port. Some of the older equipment that was designed to use ladder line and some of the other different types of transmission lines, you may see different impedances, but new equipment's probably going to be 50 ohms. Transmission lines, so the ones we're probably most familiar with is coaxial cable. Coax comes in 50 ohm, 75 ohm. I believe there's 200 ohms, so you can get it in a various impedances depending on what you're doing. Ham radio uses generally 50 ohm cable because we have 50 ohm radios. Cable TV uses 75 ohms, so it's 75 ohm cable is incredibly cheap. And if you're trying to match a dipole, it might actually be not too bad for you. So that's something to think. And then of course there's the antenna feed point. And the antenna feed point is kind of the trickiest one of the lot because this is set by the manufacturer. This is set by the manufacturer. This, just about everything within a couple of wavelengths of your antenna is going to mess with your antenna impedance. And that's kind of why this is what makes that antenna system a compromise. All right, next. All right, so we'll break it down one at a time. So when we talk about resistance of our antennas, right? It's kind of hard. It took me a little bit to wrap my mind around this because there's no resistor in your antenna. Right? What is this real component of your impedance? Well, it's actually made up of two different things. One of them is you kind of hear ohmic loss. And so that's actually imperfections in the wire. So every piece of real wire has some minimal amount of resistance to it. It's typically on the order of milliohms, but that's buried in that R there. And then you have this thing called radiation resistance. And this is actually energy being dissipated due to radiating it off your antenna, right? When you're building an antenna, this is what you want. You want radiation resistance because you want your antenna to radiate. More is better to a point, but if you have more radiation resistance than impedance of your system, now you're going the wrong way. And so you can see this is just a screenshot from my little antenna analyzer. The antenna that I had hooked up there in the middle of 20 meters has a fairly low resistance, but it's not none. So your radiation resistance is frequency dependent. It's environmentally dependent. So the earth underneath your antenna will affect your radiation resistance. Other metal objects will affect your radiation resistance. So this one's kind of fiddly to tune. And so while the radiation resistance is frequency dependent, your ohmic loss typically is not. Because the amount of ohmic loss in your wire is a function of the wire, so it's not affected by frequency. Yeah, and I mentioned, so reflections from the ground, nearby metal objects, those sorts of things will affect your resistance at HF. VHF, because the wavelength is much shorter, the region around your antenna that can affect it is proportionally smaller. But still, if you have nearby metal objects, like if you put your antenna in the attic, metal ducting, wiring, those sorts of things will affect the tune of your VHF antenna. And so this is just a plot kind of showing what my antenna looks like here at 40 meters. So this blue box is 40 meters. And so you can see this blue line is the impedance of the antenna. This yellow line or green line is the reactance. And then the red one is the radiation resistance. So you can see here in the 40 meter band, the impedance and the radiation resistance are pretty close to this 50. So this dashed line is our 50 ohm mark. I don't know if you can see, there's a zero axis that goes across here. So you can see the reactance crosses zero in a couple places. So I have a couple of resonant points here. And then out here, further out, you see the resistance actually changes quite a bit and we'll get much higher than 50 ohms. So again, just a demonstration of the frequency dependence. Next slide. Reactance. So this is kind of colloquial. I say it kind of acts like resistance, but it's not. No energy is dissipated. Now, in a real life inductor, a real life capacitor, those will have ohmic loss in them. But an ideal inductor generates reactance, and so it doesn't dissipate energy. It doesn't give us what we want in an antenna. These are probably the only two equations in the whole thing, and there's not going to be a quiz on this, but I put them up to kind of point out that when you're dealing with inductance, your reactance gets bigger as your frequency goes up. So if your inductor stays the same, that's this L, and your frequency gets bigger, your reactance gets bigger. Capacitive reactance is always negative, and it's the opposite. So if you hold your capacitance steady, as your frequency gets bigger, your reactance will get smaller. And so these two are usually playing together, and you need a special meter to be able to measure them individually, but they make up what is this X value. And then your R and your X go in to make your Z. And so these are kind of these relationships, if you kind of have a feeling for how those work, that'll help you figure out what you need to do to your antenna to kind of move that impedance point where you need it. All right. So I'll just foot stomp these bottom bullets here. So all wires have a little bit of inductance. The longer the wire, the more inductance. So if your antenna is showing positive reactance, chances are for that frequency it's too long. Capacitance gets larger as two conductors get close together. So if you have multiple wires in your antenna, that's going to provide you some capacitance. And at HF, the dirt underneath your antenna is going to provide some capacitance. So if your reactance is negative, it may be that your antenna is low to the ground, and if you raise it up a little bit, you will reduce the capacitance and pull that reactance down. So it's kind of the relationship there. Next slide. All right, resonance. So since inductive reactance is positive, capacitive reactance is negative, if you at the right values, they will add to zero. And when they add to zero, that frequency where they add to zero, you say it's a resonant frequency. There are an infinite number of resonant frequencies for any given system because it repeats every multiple of the frequency. But what resonance is not the same as matching. So in this example here, so this is my 50 ohm system, this red dotted line. So I want my antenna to have 50 ohms when it's resonant, but you can see this resonant frequency right here where this yellow line crosses zero. Well, my impedance is almost 250 ohms. So the antenna is resonant, but it's not matched. And the same thing happens, the opposite happens, right? Sometimes some resonant points, your impedance will be very, very low, and you still won't be matched, right? So the magic is right here. You can see in my antenna on 20 meters, we've got a resonance point, and then the impedance stays pretty close to that 50 ohm line across most of the band. All right, next. Standing wave ratio. So typically a lot of times you'll see this as voltage standing wave ratio because that's what's actually measured. Most of the radios I've worked on have an SWR meter, not a VSWR meter. So I use that term here. So what is SWR? And this could be another 30-slide presentation all by itself. So it's a rabbit hole, right? But when you're getting started, kind of the big picture, what does SWR tell you? It tells you how well your antenna is matched to your radio. And it does that by measuring the amount of power that's reflected off your antenna back into your radio. So in RF circuits, if you have a source with some impedance and a load with some impedance, and you launch a wave down this feed line, if this load impedance is different from your feed line, part of that energy is going to reflect off your load and come back down your feed line into your radio. Part of that will be absorbed by your load, radiated, heat, whatever. And like I said, it's more complicated than that, and that's kind of a deep dive in and of itself. But that, getting started, that's kind of the takeaway is that when you see your SWR meter going up, that means you're getting energy reflected off your antenna coming back into your radio. And when you're communicating, you want all your energy in the air. You don't want it coming back to your radio. So what isn't SWR, right? SWR isn't really a measure of how good your antenna is. So if your station is far enough advanced that you have a dummy load for testing, right? Your dummy load has a perfect 50 ohm impedance, and it will have a 1-to-1 SWR ratio. But you're not going to talk to very many people transmitting into your dummy load. So just having a 1-to-1 SWR does not mean that you have a good, efficient antenna. But it's not a showstopper, right? If you can't hit that 1-to-1 SWR ratio, that's not a bad thing. Most of our equipment is relatively robust. It's designed to handle a range of SWRs. And so that's kind of one of the trades to understand as you're going forward. And your SWR can be affected by things other than your antenna. So if you have lossy coax, because your radio is measuring reflected power, if this is lossy, that reflected wave is going to get absorbed by your transmission line. And by the time it gets down here, it's not going to look very big. So your radio might be telling you, hey, I've got a great SWR, but maybe that's your coax talking and not your antenna. Water intrusion. This is, the first time I had water in my coax, I was like, wow, my antenna is working great. It works, it's flat on 80, it's flat on 20. Turns out that water is just soaking up all that reflected power. So it makes your SWR look good, but that's because it's getting absorbed by water in the coax. So that's something to keep in mind. It's your SWR can be affected by things other than your antenna. Next. So what is a good SWR, right? And again, this is the kind of question that if you put it on an online forum will generate lots of heated feedback, right? So it's a little bit, and I might have to duck a few things here, but in general, when you're getting started, one of the things I wanted was like, why do I need to worry about SWR? So there's really two reasons when you're getting started that you need to worry about SWR. One is your coaxial cable. If you're using coax, it's typically lossy. The longer it is and the type of coax, so I've got a couple of charts here for two different types of coax, the more loss you have, right? And so when as that wave travels to your antenna, you're losing energy. And then that reflected wave coming back is also being attenuated yet again as it comes down your coax. And then if it bounces off your radio, it gets attenuated further as it bounces back and forth in your coax. So that's one of the things that's bad about SWR. The other thing is most of our new radios have transistors in their power amplifiers. Transistors don't like reflected power. And if your SWR gets too high, you can damage the transistors in your radio. Most radios have a circuit that monitors for that and will automatically cut the power to keep you from damaging your radio. But it's like wearing a seatbelt. Just because you have your seatbelt on doesn't mean it's okay to run into other cars, right? So you might keep an eye on your SWR as you're operating. And so your radio, if you look in the manual, it will tell you the SWRs that it's comfortable with. So like your ICOM 7300, it's perfectly comfortable up to about 1.5. And in fact, its internal tuner will quit when it gets to 1.5. So that's typically a good, if you can get under 1.5, your ICOM 7300 is going to be happy. You're going to be operating, you're good. It starts to walk the power back when the SWR goes above 2-to-1. And at 2-to-1, about half your power is coming back at you. So at that point, the radio will start to walk that back. And this is one I've kind of come into, because it's kind of a misnomer, right? Most of our radios come with an antenna tuner, but your antenna tuner doesn't tune your antenna. The antenna tuner would be more accurate to call it an impedance matching circuit or an automatic matching unit. What it does is it measures the impedance at the back of your radio and then flips some components in and out of the circuit to make the impedance at the back of your radio match the impedance that it's measuring at the end of your coax. So it matches your radio to the impedance that it measures. It doesn't. So the SWR mismatch still exists. It's still there, but your transistors, the output stage of your radio isn't seeing that. It's seeing a nice, comfy 50 ohm load. And so when you hit that tune button, your radio will operate just fine. And that wave that you're launching into your coax will bounce back and forth between your antenna and your tuner. And depending on the frequency you're operating on, well, now you come over here and say, well, am I worried? So if you're running RG58 and you're down at 160 meters, well, if it's 100 feet long, you're only losing half a dB. So is that a big deal? Probably not. if you're up here, on 6 meters, now your cable losses at 3 dB, you're probably losing a lot of power there having that mismatch. So, in this situation, you may want to tune your antenna a little bit better. This situation, you might be okay. LMR 400 is a lot more expensive. You can see the loss numbers are a lot lower. Same thing. So if you're running a mismatch on your, call it 80 meters, you're probably not losing a whole lot. And then as you go up in frequency, your losses get higher. So it's a trade you have to understand. How closely do you want your antenna matched to the frequency you're operating on? And it has to do with, what can your tuner handle? And then what kind of coax are you running? So what kind of losses are you going to see as that wave bounces back and forth? So tube amplifiers, they can handle reflected power a lot better. In fact, the earliest radios never worried about SWR. They were using very low loss transmission lines. They're called ladder line, and their tubes didn't care. So they didn't have tuners. They didn't worry about matching. They just got on the air and ran. And then this one comes up from time to time is, what about HT antennas? You take the antenna off your new handy talkie, you stick it on your antenna analyzer, and 2.5 to 1. Oh my God, this is a terrible antenna. But I would, I typically take the thing that your HT is low power. It's designed to work with the antenna that it came with. So if the SWR is fairly high, your power stage on your HT is going to be able to handle that. You don't have any transmission lines, right? Your radio is connected directly to your antenna. There's a little micro strip inside, but it's not very long. And then your body is part of the system. So that impedance that you see when you're holding it on your meter is not necessarily what it's going to be when you're talking on it, because of how it interacts with your body. So I tend to tell folks not to sweat the SWR on their HTs too much. But when you're getting started, it's something you can measure, it's something you can tinker with. So it's up to you. All right, next slide. Right, so the answer to every antenna question, it depends, right? There are a lot of trades that go on. And you see this online, right? Somebody says, well, what's the best antenna getting started with? And you get 3 or 4 people that immediately chirp in with, well, it depends. And then as everybody's like, oh, well, these guys are being a little bit flippant with me. They don't want to answer my question. And they did, right? Because there's so many things that affect how your antenna performs, down to the dirt, in your backyard. And some of them you can control and some of them you can't. So the best antenna depends on what you want to do, where you are, and what you're trying to achieve, right? So there is no one best antenna for ham radio. That's why I like building antennas so much, because you're never done. All right, next. So this, I was going to kind of go over just some basic antennas at a high level. This isn't how to design and build these antennas. This is just, these are the various types of antennas you'll see for different activities. And so getting into VHF, UHF, you're in line of sight propagation for the most part. And so I included these maps because one of the most important things in that frequency range is height above the ground. Get your antenna up in the air. And so this is a tool. It's called heywhatsthat.com. You can put in a point, you can tell how high off the ground you are, and it will tell you where your local horizon is with this blue line. And this will give you an approximate. It's not exact, right? Because radio waves will bend over the horizon a little bit, and a lot of things that vary, but it'll give you a rough estimate. If I'm standing at Sackett-Wright Park with my handy talkie and I'm 5 feet tall, I have a pretty good chance of communicating with everybody inside this blue line. That's about how far my radio signal is going to go before it hits the horizon. And so that's an antenna at 5 feet, Sackett-Wright. And then if you look at, our repeater antenna is almost 300 feet off the ground. Just that difference in altitude. So this is 5 watts, this is 25 watts, but just that different in altitude. Now, we're getting out to several of the surrounding communities. We can get down to Caesars Creek, all the way up to Urbana, where Ken lives. So it makes a huge difference. And if you go back to that chart, even RG58, relatively lossy at 2 meters, but that's fine. If you put 30 feet of coax between your radio and you can get your antenna 30 feet up in the ground, up in the air, you're going to gain more by pushing your horizon out than you're going to lose in loss in your coax. All right, next. All right, so antennas for FM is probably the most common operating mode getting started. By convention, FM is vertically polarized, and that's mostly because it's used in mobile applications. It's really easy to put a vertical antenna on a car. Horizontal antenna would be a little bit more difficult to mount. And line of sight, UHF, VHF polarization is important. So you don't want to try and talk to somebody with a horizontally polarized antenna if they're running a vertically polarized antenna. You're going to lose quite a bit of signal there. But I've got kind of 3 general types. So your basic, the easiest ones to build, like you can build this out of some wire and a PL259 connector. It's ground plane. It's got pretty close to unit gain. So this is about as close to an isotropic antenna as you can build easily. Works perfectly well. That's what I use at home. That's up in my attic. So when you hear me on the nets on Sunday, I'm talking at about 15 watts through a ground plane antenna. Works perfectly well. So a lot of times you'll see these base station antennas. Effectively, they're a collinear array. And what that does is now you've got multiple wavelengths of height. And by pushing that height up, it flattens the radiation pattern. So this antenna is putting a lot of radiation at high angles, which when you're on the ground and you want to talk to somebody else on the ground, you want to put most of your energy out horizontally towards the horizon. So a lot of the base station antennas are these collinear arrays that allow you to push more energy out towards the horizon, but you maintain, they don't have any directional preference, right? So you're squashing that antenna pattern down towards the horizon, but you can talk to anybody. You don't have to point those antennas. And so the repeaters, most base stations use these collinear array type of antennas. Then of course you have these, the Yagi, the beams, those are pretty common. Those need to be pointed, so you can get a lot more gain, a lot more directivity, but they're directional. So you need to be able to rotate them if you want to talk to more than one station. They're also useful for FM satellites, just to get the directivity. But again, you have to kind of point it and track that satellite as it's moving. But you know, none of these antennas are going to overcome the horizon. It doesn't matter what your antenna is, or how much power you're pushing through it. Eventually, you're going to hit the dirt, and that's going to be the end of it. All right, next. So in the UHF VHF regime, you see signal sideband, or what the weak signal digital modes. Like you can run WSJTX at 2 meters. By convention, that's horizontal polarization. You can use the same Yagi antenna that you do for FM. You just have to turn it so it's flat with the earth, and you're good to go. It's also used for folks that are, previously I mentioned like the ducting and the sporadic E, meteor scatter. There's a lot of different activities that take advantage of that, and those are all going to be horizontally polarized. All right, next. All right, so just some basic HF antennas. So we'll start with horizontally polarized antennas, just your good old dipole. They're fairly easy to construct. You need 2 quarter wavelength pieces of wire and a PL259. There are several different ways you can configure this. Kind of your ideal flat one. If you can get this up to about half a wavelength off the ground, it'll work really well. It puts your radiation close to the horizon, so you get that long distance communication. If you can't get the whole thing up super high, but you can get the middle up, an inverted V works well. It doesn't have, it puts more radiation at a higher angle. So if you're trying to talk to people closer to you, that can help sometimes. Both of these only work at odd harmonics. So if you have a flat dipole that cut at 7 megahertz, it'll work again at 21 megahertz, which is close to the 15 meter band. For those other frequencies, though, you can actually add more elements. It's called a fan dipole. And it's kind of a neat trick because each one of these elements is going to have a different impedance at whatever frequency you're operating on. Current is going to go towards the lowest impedance. And so typically, only one of these elements is going to be active at a given frequency. You run out, you can't, this doesn't go on forever. You can't have 25 elements. They eventually start to interact with each other and you have all kinds of stuff going on. But I've built them with 3 elements and they work really well. The other thing you can do for multibanding is you can move that feed point out here. You need an impedance transformer of some sort to bring that back down into the 50 ohm, but then that gives you most of the bands. One thing to keep in mind when you put up a dipole, because they're going to be fairly long at the HF frequencies, is they don't have to be perfectly straight. that's the pictures to show you in the book, but the center piece right here by the coax is going to be your most critical section because that's where the current is the highest. But once you get out here, you can kind of bend these ends around however you need to fit them in your space, and it's not going to affect the antenna a lot. And that kind of goes for all of these. And these antennas can be strongly affected by the ground. I've noticed a difference in mine just when it rains because the reflectivity of the dirt changes when it absorbs water. And part of that radiation resistance you see is the wave as it bounces off the dirt, comes back up and interacts with your antenna. So they are fairly, and that's kind of the one thing you really can't do much about in your backyard is the dirt that it's made out of. Next. All right, so vertical antennas. These are vertically polarized. I guess I should have started off with HF communications. Polarization is not as critical because skywave, your radio wave goes up into the ionosphere and it gets twisted and split and bounced around and it comes down. Some of it's circularly polarized, some of it's linearly polarized, but you don't see the polarization mismatch losses that you do at VHF and UHF. I can talk to a guy on a vertical with a horizontal dipole, typically without issue. Sometimes you'll hear what's called fading, and that's as that polarization is distorted by the atmosphere, it'll move back and forth between vertical and horizontal or circular, and you'll hear what sounds like their voice disappears for a second and then comes back up. But in general, you can communicate with folks without having to worry about the polarization of your antenna. So verticals are good if you don't have any trees. You don't have to worry about getting your vertical antenna half wavelength off the ground. But you do have all these radials that you have to deal with. You can lay them in the grass, and I've heard that if you put them down in the spring and let the grass grow, they end up down below the grass, and then you don't even know they're there. But the radials will affect how well your antenna works, and it affects the impedance matching. Again, depending on the frequencies you want to work, they can be quite tall. So if you want to work 80 meters with a vertical, you're getting into 30, 40 feet tall. Next. Loop antennas. So there's generally two types of loops. So the illustration here is a sky loop. They're about a wavelength in circumference. They don't have to be round. This one's square. They can be diamond shaped. The impedance depends on where you connect your coax. If you connect it at a corner, it's going to be about 200 ohms. If you connect it down one of these legs, the impedance starts to drop, and a lot of times you can find a 50 ohm spot. The antenna book goes through all the math if you want to build one. And then you have these compact loops. So these compact loops are going to be the circumference is going to be much, much smaller than a wavelength. So they're very handy for small spaces. They're not as affected by the ground, so you don't have to have them up super high in the air for them to work. But they're going to be very narrow bandwidth. And that's because they require a specialized tuner. So the tuner in your radio is not going to be able to tune a loop. And in fact, you can see this picture, this little black knob here, that's connected to a big capacitor. And as you change frequency, you need to change that capacitor so that your antenna resonance, your impedance follows you as you go up and down the band. These are very nice receiving antennas because that very narrow bandwidth cuts out a lot of noise. But you're typically limited in power, primarily because that capacitor can only handle so much power. So big high power loops are very expensive. So most of these small portable loops are limited to 10 to 15 watts. I think this one, I think you can get them up to 100 watts, but you don't typically see compact loops like this that can run at full legal power. All right, next. All right, so questions, rotten food. That's my. And if folks are interested, we can pick some of these and do a deeper dive into them. So just send me any feedback you have, or if you have any questions, be willing to see what I can say.
Come on, folks, you have to have questions, at least one.
All right, well, I got one.
Okay, good.
So you got the butternut up there in one of your photos with the vertical.
Yeah.
Do you ground that vertical at the antenna mounting point and or at the entrance to the shack?
Grounding and bonding is another rabbit hole.
Well, I'm brand new, so
Correct.
Gotta start somewhere.
And so there's really two different things going on here. So for a vertical, you have those ground radials that are part of the RF system. They affect how your antenna radiates. And then because you have a giant tower sticking up in the air, it's going to get struck by lightning. So you have the grounding, bonding portion of that is a safety portion so that you try and minimize the damage. Direct strikes are going to destroy everything, but you try and minimize the damage. So generally you want a lightning arrestor out by the antenna and then one before it comes into the house. And so that's the safety grounding portion of that. But that's separate from the ground radial field. They're tied together, but functionally they do different things. Yeah. Glenn?
I've got a vertical and it's got probably the minimal number of radios. I've got a vertical and I'm using the minimum number of radials on it. And it's working okay, but I'm sure it can work better. So my question is the length of the radials, is that really critical? Or is there a formula for figuring that out? Or can I just start adding a bunch of wire?
Yes, there's a formula, and actually the ARRL antenna book has kind of a plot that shows you, how your antenna performs as you increase the number of radials and the length. Typically what I see is if you have a multi-band vertical, you'll have some radials cut for different frequencies. Radials, there's a diminishing return. At some point, doubling the number of radials doesn't double the performance of your antenna. And you run into that pretty quickly. I think the chart that I saw in the antenna book it starts to flatten out around 60. But then it is already fairly flat at that point. So I think I've seen somebody say that the difference between a perfect electric ground and 30 or 40 radials is about 3 dB performance wise. So
part of my radials are limited because of where they're at in the yard. I come to my neighbor's property and the radials stop.
right.
So if I go in and check and put more of them in just east and west instead of all the way around, will that gain me anything? If I can get
Yes.
the correct length, but it's not.
It will, and what you'll find is it starts to be more directive along the axis where you have those longer, denser radials. Some of the portable verticals you see will have a single radial,
Right.
and it'll actually be more sensitive in the direction that radial is pointing. So it doesn't have to be uniform, but if it's not uniform, that does affect the pattern that you'll get out of your antenna. So if the fence line is running north and south, your antenna will work a little bit better north and south than it will east and west.
Thank you.
Not yet, no.
Well, thank you. Appreciate that. Very good. Very interesting. Well, you asked about antennas and he told you everything you ever wanted to know about antennas. So thank you very much. I came up with another topic we might want to talk about someday, and that's the rabbit hole called grounding and bonding. You can really go down the hole in that one. If you ask 10 different people about how to properly ground and bond, you'll get at least 13 different answers.
I think Newham, I support that question completely.
Okay.
Totally confused.
Good. All right.
The ARRL has,
Joe was going to speak.
the ARRL has a manual called Grounding and Bonding. Okay, and when it was introduced, the author talked at one of the conferences about it, and he got someone in the audience who really complained because he didn't have any technical references to what he was saying in the book. So there's opinion about bonding and grounding.
And
Yeah, that was Ward Silver. I have his book and my house is grounded according to Ward Silver. Yes, John.
and we also have that book in the Burke Library if you would
Yes.
like to check it out.
So lots of interesting topics about ham radio, all of which we all agree completely on every topic. Yeah. So on that note, I want to thank everybody for coming in. When you leave, please leave your name tags We'll keep them together. So when you come back next time, everyone will have them and will know who you are and you know who your neighbor is. So thank you for coming. I'd like to take a motion to close the meeting. Okay, we have and a second. Okay. Larry made the motion, and who do we have over here? Ken second, and we also have our greeter second. So we have thirds. So I think the motion carries. We're closed for the night, but before everybody goes, I'd like to see Jim, John, Roger, and Jackie before you all leave. Thank you very much and have a good evening.